Hi, Dr. P here, and in this lecture we're going to take a look at molecular shapes. Why do molecules have the shapes that they have? Well, why are we interested? For one thing, well, we want to know the three-dimensional structure of molecules because that's going to be the key to their function. And how are we going to determine structure? Well, what we're going to use is something called valence shell electron pair repulsion theory. Otherwise called VSEPR, sometimes pronounced Vesper. And the main postulate of the valence shell electron pair repulsion theory is that the structure around a given atom is determined principally by minimizing electron pair repulsions. So we'll say here, say structure around an atom determined mainly by electron pair repulsions. And now it doesn't matter if the electrons are a lone pair or a bonded pair. So I thought what I would do is I've got some models here, and I also have, this is figure 7.16 from the text. So I'm going to zoom in a little bit here. So you guys can maybe see that a little bit better, and we'll take a look at some different cases. The first case is if we have two things attached to a central atom, and that's what we have here with BeH2. So we have just two things attached to the central atom, and in that case we get a linear arrangement with a 180-degree angle between our bonds. We call that a 180-degree bond angle. So it's our bond angle there. And so what that looks like with a model is this guy here. We have our central atom, we've got our bonds, which are these kind of lobe things, and we'll talk more about that in the next chapter. And then we've got our atoms at the ends of the bonds. So this is a linear shape or a linear geometry. Sometimes geometry is used instead of the word shape. Next, if we have three things attached to our central atom, then we have what's called trigonal planar, where our bond angles are 120 degrees. And so that's going to look like this. Now in both these cases, these pairs of electrons, they're in bonds, but they're still pairs of electrons, are trying to maximize the distance between them. So it's not going to be any, we're not going to have any more, because then these two would be too close if, this was trying to get further away. So this maximizes the distance. Our trigonal planar geometry maximizes the distance between our pairs of electrons in the bonds. Now if we have four things, we don't get a square structure. Instead we get something called tetrahedral, which is this guy here. This is our tetrahedron. We have our central molecule, and this bond angle is 109.5 degrees. I once had a calculus problem set that had a problem where we had to basically prove that the bond angle in methane was 109.5 degrees, and I could not do it. But anyway, we don't have to worry about proving it, we just know that it is. And so one thing to note is how this is drawn. Okay, so this is the orientation of the molecule right here. So these two bonds and their hydrogens are in the same plane as the central carbon. And then we have one hydrogen in its bond, that's the dashed bond. It's going away from us. And then this solid wedge bond is coming out towards us. So let me just draw that again here. See, we've got a wedge, an H, 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 dashes with an H. And this is out towards us, back away from us, and then in plane. Okay, so this is the type of drawing that you're going to be doing when you draw three-dimensional structures. You need to use this wedge and dash notation or formalism, whatever you want to call it, but you need to use the wedge and dash structures when you try to draw a three-dimensional structure. It's just a nice format for doing things so that everybody in chemistry understands what they mean. All right, now if we have 5 things attached, we get this kind of funky structure here, where we have 3 atoms around the middle, and then one above and one below. And if you look at it, it's a triangle, and it makes sort of a pyramid. If I take the bottom off, you can see, yeah, that's a trigonal pyramid. And so we call this trigonal bipyramidal, or bipyramidal. So trigonal bipyramidal, so triangle in the middle and then top and bottom. And these atoms could be attached in, the ones around the middle are called equatorial. They're like around the equator. And then axial are above and below. They're on the axis if I spin this guy on its axis. So this is what things look like if there are 5. If there are 5 things. This is what a molecule looks like if there are 5 things bound to it. Now in this case also, we've got 2 different bond angles. Between the equatorial atoms, we have a 120-degree bond angle, so between the fluorines on the equator here. Between the axial and an equatorial, our bond angle is only 90 degrees. So we actually have 2 different bond angles, but that's what it takes to maximize the distance between these pairs of electrons. Then our last case is where we have 6 things attached to our central atom. Like here we have SF6, and this is what we call octahedral. It's an octahedron. So we've got 4 around the middle, 1 above and 1 below, but I can turn it like that. All of these angles here are 90 degrees. This is very symmetric. It would be an 8-sided die if you had the solid surfaces, solid faces on it. And yeah, all of these angles are 90 degrees, or if they're opposite each other, it's 180 degrees. So this is the octahedral. Okay, so let's go ahead and let me just, sorry about that, let me find a highlighter. Let me find my highlighter. Let me find a highlighter. I'm looking in the drawers that I got this new desk a few months ago, and I can't, there are the highlighters. There we go. I can't remember where I put everything in the desk. Okay, so we have linear for 2 things attached, trigonal planar where we have 3 things attached, tetrahedral where we have 4 things attached, Trigonal bipyramidal is 5 things attached, and octahedral is 6 things attached to our central atom. So you do want to get used to drawing these types of structures. So like I did here with the tetrahedral. So definitely practice drawing these. When you draw Lewis structures, start drawing them like this. Okay? You know, you can go ahead and space your, you know, like I did with nitric acid here. There's a reason why last time with nitric acid I made it look like that, because it's trigonal planar. It's got 3 things, even though one's a double bond, it's still just one atom. 3 atoms attached to a central atom, so it's going to be trigonal planar. And yeah, I just sort of naturally do that. I start showing the, shape in my Lewis structure so that, you know, you get a little bit more information. All right, so those are our overall molecular shapes. Now, things can get kind of interesting because we can have molecular shapes versus electron geometry. And so a molecular shape is simply the shape of the molecule. An electron geometry, however, includes the lone pairs that may be present in the molecule. So for example, if we have NH3, ammonia, if we draw the Lewis structure, we'd see, let's see, we've got 5 electrons from nitrogen, and then 3 from the hydrogen, so 8 total electrons. So we have nitrogen, H, 2, 4, 6, and a lone pair. So we could draw this, nitrogen, H, we'll have one H coming out in front of us, and one hydrogen going back away from us, sorry, not out in front, but out towards us. And then that lone pair, the nitrogen and the hydrogen, are all in the same plane. So what does that look like? Well, it looks like this guy here. Okay. And I realize now I have been drawing. I do apologize. Let me just zoom out again here. There we go. Sorry about that. Maybe one more. There we go. Sorry about that. I forgot to zoom out when I started drawing things again because I had zoomed in on that figure. Anyway, so molecular shapes, we're going to ignore lone pairs, but electron geometries, we include them. So we're looking at ammonia, which has a lone pair. And so its electron geometry is tetrahedral. You can see this is a tetrahedron. This is the lone pair right here in some kind of orbital. So my electron geometry is tetrahedral. But my molecular shape, we ignore this guy. So I'm just going to cover it up. In fact, I'll take it out. What do we have here? Well, we have, it looks triangular, so it's trigonal, but it's not flat, it's not trigonal planar, it's a little pyramid. So this is trigonal pyramidal. Put my lone pair back in there. All right, so we have a certain electronic geometry, and so the electron geometry for methane is the same as the electron geometry for ammonia. But methane, the molecular shape is still tetrahedral, but for ammonia it's trigonal pyramidal. Now we can do this with additional molecules, like let's say we had water, H2O, with 2 lone pairs. This again is a tetrahedral. Here's my tetrahedron. This is a tetrahedral electronic geometry. But if I cover these guys up and just focus on what I have here, this is or if I just pull them out, this is a bent molecular shape. So there is a nice table that summarizes all of these, and I'll go through them with you guys here in just a minute. But we have figure 7.19 goes over all the different shapes here. So the key here to remember is that we have our electron, it says here, electron region geometries. And this is actually a really good point here. The molecular structures are identical to the electron pair geometries when there are no lone pairs present. That's the first column. So I like to think of how many things are attached to a central atom, and things can include lone pairs. So it's a bonded atom or a lone pair. And that gives us our electron geometries. Now, if we don't count the lone pairs, then we get our molecular shape. So you can almost think of these, a number of electron regions. This is the number of things. Number of things. Okay, and these are kind of like the families, if you will, and then there are different cases of molecular shapes within each family. So obviously for the simple one here, we just have linear. If we had one lone pair, it would still be linear, so not really that interesting. For trigonal planar, no lone pairs is trigonal planar. One lone pair, so I have a pair of electrons here. One lone pair, our shape is bent. Okay, so just imagine a pair of electrons here. Now we've looked at the tetrahedral with 4 bonded atoms. When we have one lone pair, we have trigonal pyramidal. And then with 2 lone pairs, we have bent. There's my bent molecule. Now for 5 bonded atoms, we have trigonal bipyramidal. And so if I have 4 and 1 lone pair, I don't get a trigonal pyramid, I actually get this seesaw. The text also calls it a sawhorse, but you can see seesaw back and forth. So it's this kind of interesting shape there. And that's if there's 1 lone pair. If there are 2 lone pairs, I'd have a lone pair here, and I get a T-shape molecule. Looks like the letter T. And then lastly, if I had 3 lone pairs, they'd all be around the middle. It turns out that the lone pairs exert a little more repulsive force than the bonded pairs. So for example, in something like water, these guys are pushing away from each other a little bit more, and these are pushing a little closer. So the bond angle in water is more like 104.5 instead of 109.5 degrees. So the best way to minimize the energy is to have those lone pairs all around the middle for our trigonal bipyramidal electron geometry. Having the lone pairs around the middle minimizes those interactions because we get those nice 120-degree bond angles, and we have a linear molecular shape. All right. Now, the last case is our octahedral case. And in the octahedron, if we have one lone pair, so there's our lone pair, we have a square pyramid. Notice how that sits there, it's square, but it's a pyramid. Square pyramid. If we have two lone pairs and four bonded atoms, we have a square planar, all in one plane, a square planar molecular shape. If we have three lone pairs and three bonded atoms, we have T-shape. So this is kind of like the T-shape in the trigonal bipyramidal electron geometry, but it's octahedral. So 1, 2, 3 lone pairs and 3 bonded atoms. My atoms are falling apart here. And then, of course, if we have 4 lone pairs, they're all around the middle, and we get a linear molecule. So you will want to familiarize yourselves with these shapes. You'll get to work on these in making models in a, not quite like this. You'll use, instead of these lobes here, you'll have plastic sticks to represent the bonds. And so you'll get to play around with that. And yeah, that's molecular or electron and molecular geometry. So how we describe the shapes of molecules. Now, what if we have a molecule that doesn't have one single central atom? Well, then we look at each of those middle atoms individually. We have sort of local geometry. And then the other thing to think about is how well does this model work? And it turns out it works pretty well in most cases, but it fails in some cases. For example, ammonia has a bond angle of 107 degrees. Ammonia is NH3, but if we look at phosphine, PH3, its bond angle is 94 degrees. So it's considerably different. And we can add some rules to the relatively simple VSEPR model to improve how well it works, but we're just going to stick with the model as it is. And so the last, this is the last lecture for this chapter. In the next chapter, we will look at the reasons why we get these shapes, and we'll look at some explanations for how atoms bond the way they do. So we'll get, instead of just a description of the shapes, we'll look at some of the reasons behind the shapes. All right. Well, practice drawing your different molecular shapes, and I will see you guys later. Stay safe out there. Bye now.